Hello guys, welcome to today's lecture. In this lecture, we'll quickly derive these expressions. Average energy per particle for relativistic particles, and then for non-relativistic particles. These non-relativistic particles we already derived in the last lecture. This rho is equal to m plus 3t by 2. Rho divided by n is m plus 3t by 2, and that's what we are saying here. And then we'll drive a term expression for the pressure. Again, everything using Mathematica. Okay, so how do we get this average energy per particle? We have the expression for the energy density divided by number density, and this energy per energy this is using Mathematica, so those are variables using Mathematica. Energy per fermion per number of energy per fermion particle, energy per boson particle. So this is energy per fermion particle, energy per boson particle. So energy per fermion particle, if I go to my last Mathematica file, energy density fermions, this expression, energy density fermions, and then energy density bosons, because I changed the name of the variables, so I am going to do the changes here also. Energy density fermions, and then I have energy density bosons. Okay, then NF is number density of fermions, which I derived here. What was the variable name? This I derived in my previous videos. Energy density n fermions and n bosons. N fermions and bosons. So you have in lecture number this n fermions, and this is n bosons. Right. So when you evaluate this energy density fermions, which I derived it's a variable, I calculated this in my last video, and fermions, I calculated this in my last video, energy density bosons and bosons. Then you do it using Mathematica or straightforward. Basically, you are this you already know from the last videos, and just divide the two, you get energy per particle. So energy, yeah, and then because you want to see the numbers, if you want to see the numbers, you need to call the function n, and will give you the numeric value of whatever you get here. So from here you get this, and then you say /n/n, you get this. So energy per particle in the relativistic regime is this for fermions, this for bosons. Now for non-relativistic particles, pretty straightforward. We saw in the last video, rho is equal to m plus 3t by 2n, and energy per particle is given by rho over n is equal to m plus 3t by 2. Okay, now pressure. Relativistic, very straightforward. Pressure, this C. C is pressure in the relativistic regime. Again, pressure is given by this expression, P square by 3E Fp. And what is in the relativistic regime, Fp? This is the expression for pressure in both relativistic and non-relativistic regime. Now we need to plug in E and Fp in the relativistic regime. E is P, Fp is 1 over e to the power p over t plus minus 1, and dqp becomes 4 pi p square dp. And this is straightforward from the. Now you can solve it using Mathematica, or you can look at the integral that we obtained in the expression of rho. So this integral is if we factor out 1 over 3 outside, the remaining integral is same as what we obtained in the expression of rho for relativistic in the last video. Rho for relativistic. I think this is, yeah, so this is a expression which we obtained in the last video for energy density in the relativistic regime. And here we only have 1 over 3 additional factor. So you can say that pressure is equal to rho over 3 in the relativistic regime, and we get same whatever we get in the relativistic regime, energy density, and divided by 1 by 3. So the same expression of rho here divided by 1 by 3. So we get this thing. Now in the non-relativistic regime, we would like to look at this. In the non-relativistic regime, we want to look at this thing. Okay. So pressure is given by, this is the expression for pressure. We plug in energy in the non-relativistic regime, m plus p square over 2m, and rest is like blah 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 blah. Energy is plugged in, replaced with m plus p square over 2m, and dqp is replaced by 4 by p square dp, and 0 to infinity. You can solve it using Mathematica and just set up the integral and then use Mathematica. Using Mathematica. Okay, this is not a course on calculus. So, by the way, you must have seen these integrals in various forms in your undergraduate course in statistical physics. Pretty straightforward, blah, 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 integrals, and then it gives you this. So, pressure non-relativistic is this thing. And what do we get here? So, we get here pressure non-relativistic is this. And after you do factoring out, you get this, and then you see in the, we have this term 2m minus 5t. In the non-relativistic regime, 2m minus 5t is approximately equal to 2m, because we are in the non-relativistic regime. And so after you do like algebraic manipulation, and you get pressure is this. And when you divide it by number density non-relativistic, which we have seen in our previous videos, number density non-relativistic. Where is number density non-relativistic? We have seen in our previous videos that the number density non-relativistic is given by this expression. And then you divide number density non-relativistic, and then you see that finally you get pressure is equal to nt. So pressure is equal to number density non-relativistic, and by the way, this is all Mathematica, the gray, using Mathematica, and this T is the output of Mathematica. So pressure becomes nt. In the non-relativistic regime, pressure is equal to nt. And what do we have? Rho in the non-relativistic regime. Rho in the non-relativistic regime is this. This is rho in the non-relativistic regime. and recall that rho is equal to this in non-relativistic regime. So see that pressure, this is approximately equal to Nm. So we have Np pressure, and density is Nm, and Nm is definitely higher than Np in the non-relativistic regime, because in the non-relativistic regime, mass is higher than mass is much higher than much higher than temperature. So Nm is much higher than Np. Therefore, rho is much higher than pressure. So pressure is almost negligible in the non-relativistic regime. So for non-relativistic particles, pressure is almost negligible as compared to density. Anything else? I think we covered everything for this video. Thank you very much, guys. Bye bye. Take care. See you next time.